Hey everyone, and welcome. So today, we are going to dive deep into the absolute heart of an airplane. Yeah, the part you're actually sitting in, the part that holds literally everything together, the fuselage. You can think of it as the main body, the spine, the very core of any aircraft. And believe me, it is an absolute masterpiece of engineering.
I mean, really think about that for a second. When you're cruising 7 miles above the surface of the Earth, what is actually stopping the wings, the tail, the engines, and, you from all just going their separate ways? Well, the answer is this one single incredible piece of engineering.
So the official definition is pretty straightforward. It's the central body of the aircraft. But it's so much more than just a big tube for people and luggage. It's the structural hub of the entire thing. I mean, everything. The wings generating all that lift, the tail keeping it stable, is physically bolted right onto this central structure. It has to handle all of those incredible forces all at once.
Okay, so how on earth is something so strong actually built? Well, to really get it, we need to kind of peel back the skin, literally, and take a look at the engineering evolution that's happening on the inside.
See, way back when, there were two main ways of thinking about this. Over on the left, you've got the truss type. This is basically a rigid internal skeleton, usually covered in fabric. Think of an old biplane, right? But on the right, well, that's the idea that changed everything, the skin stress type. This is where the outer skin isn't just a cover, it is the structure. And that one concept, it became the foundation for all modern aviation.
So the first version of this new idea was the monocoque structure. And monocoque is just French for single shell, which is the perfect description. The outer skin carries all the load, and it's just shaped by these internal circular frames. Now, it's incredibly strong for its weight, but it's got a big weakness. Because the skin is doing all the work, one significant dent or a bad crack could compromise the entire structure. Not great. And that weakness brings us to the design used in pretty much every single modern aircraft today, the semi-monocoque. This is just a brilliant solution. It keeps that strong outer skin, but it adds a really robust internal skeleton to help out. You've got these powerful beams called longerons that run the whole length of the fuselage, and they're connected by smaller supports. So now, the load is shared between the skin and this internal frame, which makes it unbelievably resilient. It's a team effort.
All right, so now we get the internal structure. But what about that iconic shape of the fuselage itself? You might think it's all about pure aerodynamics, right? Well, it turns out the design process actually starts from the inside and then works its way out.
And here's the key takeaway. The payload, what the plane is built to carry, is what determines the shape. The fuselage is really just the most aerodynamic wrapper you can possibly put around that payload. For instance, a UAV might have this weird whale shape because it needs to cover a huge antenna in its nose. Or for a passenger jet, the diameter comes down to how many seats you want to fit across, how wide the aisle needs to be, and how much cargo you want underneath. The mission always comes first. The shape just follows.
So once engineers figure out what needs to go inside, they start to optimize the outside shape using this really important metric called the finest ratio. It sounds complicated, but it's super simple. It's just the length of the fuselage divided by its widest point. Getting this ratio just right is a critical balancing act between cutting down on drag and making sure the aircraft is stable.
Now this is where it gets really interesting. Look at how dramatically that perfect ratio changes with speed. For a regular subsonic jet, a shorter, kind of stout ratio of about 6 to 8 is the sweet spot. But once you start pushing past the speed of sound, you need a much longer, almost needle-like shape to slice through the air. A ratio of 10 to 15 or even more, like the Concorde's insane 16.7. This is a perfect visual of physics just doing its thing. Okay, so we've got the structure, we've got the shape. Now for the most critical part of all, making sure it doesn't break. This is a super high-stakes puzzle where engineers have to figure out how all those forces actually move through the structure when the plane is in the air.
And believe me, the stakes could not be higher. Like aerospace engineer Todd Coburn says right here, just making simple assumptions, like assuming the entire skin of the fuselage carries its load perfectly equally, is just dangerously wrong. It gives you answers that are unconservative, which is basically engineer speak for way weaker than you think.
And the whole problem comes down to this concept called the effective width of skin. So think about it. When a fuselage bends in the air, the top part is often pulled tight. That's tension. And the bottom part is squeezed. That's compression. Skin under tension is great. The whole sheet works hard. But skin under compression, it tends to buckle just a tiny bit, which means only a small part of it, right next to those internal supports, is actually doing the work. So yeah, not all skin is created equal.
So how do you solve this? You can't just guess. Engineers use this really painstaking process. First, they run all the numbers assuming all the skin is working perfectly. That's their starting point. Then, they look at the results and see which parts are getting squeezed under compression. For those areas, they basically tell the computer model, okay, the skin here isn't working as hard, and they reduce its effective width. Then, they recalculate everything. And of course, the forces all shift around. So they find the new compression spots, adjust again, and recalculate over and over and over, until the whole stress model finally stabilizes.
And the result of all that work is, well, it's staggering. In one example calculation, the first, overly optimistic guess showed a maximum stress of about 11,000 pounds per square inch, or 11 ksi. But after going through that whole loop to account for the buckled skin, the actual stress on that exact same part was 29 ksi. That's 29,000 pounds of force on every square inch. It's almost 3 times higher than the first guess, and it just perfectly shows why this incredibly detailed work is the difference between a safe design and a total disaster.
So, you see, the fuselage is so much more than a simple tube. It's a complex semi-monocoque structure. Its shape is dictated entirely by its payload, and its strength is double and triple checked with this meticulous iterative process. So, the next time you're sitting in a window seat looking out at the wing, I hope you'll also think about all of this incredible invisible engineering that's holding it all together. Thanks for watching.